Okay, Joel, you're ready? So we'll start. So welcome everyone to today's ICTS monthly colloquium. We are still in the online mode, and we are very happy to have Professor Joel Moore from the University of California at Berkeley giving the talk today. And it's unusual time, but given the time differences, thank you, Joel, for agreeing to give this late night talk for you. Professor Joel Moore is Chern Simons Professor at the University of California at Berkeley in the physics department, and also a senior faculty member at the Lawrence Berkeley National Lab. And Joel has been one of the leading contributors in the field of strongly correlated systems. And in particular, the area that I am most familiar with is his contributions in the area of topological phases, both what is now known as symmetry protected topological phases and long-range entangled symmetry enriched topological phases. And apart from that, he has been working on a large number of other things, various areas of quantum magnetism and transport in strongly correlated systems. Joel completed his PhD from MIT and then did his postdoc at Bell Labs before joining Berkeley. But he's very well known in the TIFR family. He spent a year in TIFR, I think in 90s. And so a lot of people in TIFR know him apart from his physics. Without further ado, Joel, it's over to you. Thank you again for the talk. So just a moment. So please mute your mics. And if you have a question, you can unmute yourself and ask a question. And if it is pressing, and at the end of the talk, we of course would have a discussion with Joel. Okay, please.
Great. Thanks very much for the chance to give an ICTS colloquium, even remotely. I hope that we can all get back to visiting soon. I've certainly enjoyed my visits to ICTS in the past. So most of this talk is about if we have a topological phase of electrons, and I'll remind you what that is, often that generates some kind of unique electromagnetic response, which we could hope to measure. And in fact, sometimes these responses are related to things that people have talked about previously in particle physics. And what I want to build up to in sort of the main part of the talk is what we think might be the first example of a quantized nonlinear response in a solid, and how that is sort of seen experimentally and how it's related to things that you might have heard about before. So this kind of teaser equation I have on the slide there, the one on the left is the two-dimensional current density induced by an electric field in the quantum Hall effect, dropping indices. And the one on the right is this candidate response in certain Weyl semimetals. And I'll talk about what those are as I go along. And the nice thing about this physics is that it's an appearance of topology outside where you would expect, but it doesn't actually require a great deal of technical background or heavy lifting. You can understand most things in sort of a one electron picture with some perturbation theory. So that will be the main part of the talk. But then at the end, I wanted to give a bit of an update on what is in some ways a harder problem, which is fractional topological phases, and in particular quantum magnetism. Because just in the last year or so, there are some neat methodological changes, I guess, in the field. At least they seem like changes to me, and I've been doing this for a while now. So I thought I would just mention those. And as a result, I think I took out one thing that was in the abstract maybe, which was a little bit on magnetic Weyl semimetals. So I'm not going to cover that, but if you do want to know about that, just ask me at the end maybe. All right, so the high level picture is, as I said, how do topological materials give interesting responses? And in particular, the two things that are unusual about the one we're going to focus on are that, first of all, it's in a metal rather than an insulator. Normally in metals, we don't expect quantization, and I'll remind you why. And second, it's not a sort of adiabatic zero frequency limit. It's actually a relatively high frequency optical effect. And why we had to look there took a couple of years for us to figure out. So I'll kind of go into the background, but basically, ever since Weyl semimetals were discovered, it was natural to look for things analogous to the chiral anomaly in particle physics, which was a known special property of Weyl semimetals. But it turns out, yeah, that's somewhat difficult in practice, so you wind up being led to consider other things. And I will talk a little bit about interactions and how it's similar and different from graphene. But maybe the general sort of higher level question to keep in mind is, when can there be quantization in gapless systems and even in metallic systems? And how is it different from what we're used to? It's certainly weaker, and the maybe microscopic origin of the quantization tends to be a little bit different. But I'll remind you of one example in just a slide or two to kind of make you think that this is believable. And then, as I said, I'd like to spend the last 10 or 15 minutes on how the search for spin liquids, basically fractional topological phases made up of spins, has changed a bit in the last year or two. And I will talk about some work of ours, but also about some other things happening in the field. So when I say that there's quantization in semimetals, that might sound bizarre, but here's a simple example. It is quantized in terms of elementary constants, although not at the level of 1 part in a billion or something, but at the level of about 1 part in 100. And what I wanted to mention is the easiest way, I think, to measure the fine structure constant, this famous number 1/137 that we all like, at least if you have a friend who can give you a big sheet of graphene. If you can get the big sheet of graphene, you can hold it up to the light, and you'll see that it's mostly transparent. Most of the light gets through, but a little bit of the light gets blocked, about 2.3%. And that 2.3% is pi times 1/137. In other words, it's pi times the vacuum fine structure constant, more or less. It's the velocity of light that appears here, not the velocity of the relativistic electrons in graphene, the linearly dispersing electrons in graphene. So this effect is not very topological, and it only applies over some intermediate range of frequencies that happen to include the visible. But it does show that just because a system is a metal, and in particular a semimetal, because remember, graphene doesn't have a big Fermi surface, it just has Fermi points. Maybe there are some special possibilities where our conventional wisdom no longer applies. So the materials I'm going to build up to are these so-called Weyl semimetals, which are one way of, if you like, generalizing graphene to 3 dimensions. And the idea of these goes back at least to the 1930s. And it's nice from a maybe fundamental physics point of view that the electrons in these materials are like Weyl fermions. They have a handedness. It's like I broke up a normal Dirac electron into a left-handed part and a right-handed part. And we now believe that there are not Weyl fermions like that in the standard model of particle physics. So we have them as emergent particles. Discovering neutrino oscillations kind of ruled out that they might exist, at least in the standard model, as fundamental particles. So that's maybe saying we've had Weyl electrons in solids since about 2015. But the hard part until recently was, so what? You know, what is the emergent effect or response that you get because of the Weylness? There are a few examples, but I'm going to talk about one that I think is as fundamental as any other. But maybe before I get to our favorite effect, it turns out that even sort of standard nonlinear optics, just like apply light at frequency omega and measure how much comes out at 2 omega, frequency doubling, are incredibly strong in Weyl semimetals. And I'll flash up a bit of data later, although this is mostly a theory talk. But basically the point is, it seems like nonlinear optics in these materials, without even trying, are strong in general. And then there's one particular effect that is not just strong, but quantized for somewhat interesting reasons. But linear optics, conversely, is not really good enough to see anything very uniquely Weyl, at least in zero magnetic field. We have a mild sort of no-go theorem there. Okay, so that's kind of where we're going, but now is probably a good time to back up a bit. Just in case I forget at the end, these are maybe the main people involved, both theorists and experimentalists in the main part of the talk. And then at the end, there are some people currently at Berkeley. The people in the top row have all moved on. They were all either postdocs or students at Berkeley who are now scattered around, but they were certainly a pleasure to work with. And then there is a 3-way experimental collaboration that led to the partial confirmation that I'll show you later on. All right, so now let me give a colloquium style introduction maybe to why we care about topological phases and how they fit into sort of the standard model of condensed matter physics, I guess. So I would say the standard model of condensed matter is about symmetry breaking, where until about 1980, we could classify the kinds of order that we ran into by what sort of symmetries were broken. So a simple example would be a crystal has a lot of rotational and translational symmetries, but it's got fewer than the vacuum, which has continuous rotations and translations. All the other phases, at least on some level, could be thought about in terms of breaking of a symmetry, not just crystals, but liquid crystals. Magnets, you could think of as breaking a direction in spin space or picking out a direction in spin space and also breaking time reversal. Superfluids, in a sense, break a symmetry as well. So this was a very successful picture. And of course, not just a philosophical picture, but an actual quantitative tool. So universality of second order phase transitions, which I'm not going to repeat in detail, but this is really what made me want to be a condensed matter physicist when I heard about it, which is that, for example, I can look near the liquid gas transition when that disappears at a critical point in a fluid like water. I can measure how it disappears and find a critical expo. The density difference between liquid and gas vanishes like a power law of the temperature difference from the critical point. I can similarly measure how the spontaneous magnetization of iron goes away as I get close to the Curie temperature, where it becomes a paramagnet. And the magic is there's a kind of universality where those exponents are actually the same, even though one of these systems is a fluid of atoms and very classical, and the other is very quantum mechanical and made of electrons. So topological phases have a different sort of universality, but it's appealing in kind of the same way that you can sometimes have one description that describes a lot of things with different microscopics, but those microscopic differences don't matter very much. So that's where we're going. But first, how does it still tie into symmetry? Well, in general, the symmetry analysis of condensed matter is still correct. Symmetry in general tells us if a response is allowed to be there in a given solid. So for optics, because most theorists, I think, don't think a whole lot about optics maybe, here are some relevant symmetries. If I break inversion, like in gallium arsenide, then that allows me to have a response that is nonlinear in applied electric field, specifically as the second power, and that gives me second harmonic generation. Now, polar materials, we use that term to mean a subset of inversion breaking where there's actually a preferred vector. So for example, gallium arsenide breaks inversion, but it has a lot of threefold symmetries and so on that don't allow any one particular direction. If you wanted to make a solar cell or something, then you wouldn't use gallium arsenide. You would use something that was either as a crystal or fabricated to have just one direction that the current would flow along when you shined light on it. Chiral materials are another subset of inversion breaking where I don't have any mirror symmetries. And those come up later on. They allow optical rotation. Light can pass through and have its polarization plane rotated, even if the material doesn't break time reversal. So some kinds of quartz are an example of that. So it's still true that symmetry generally tells you whether something is allowed. And if it's allowed, it pretty much has to be there, according to Landau. But where the topological aspects can come in is that they give you a magnitude of some effect that is basically independent of microscopic details. And it's also true that understanding the topology and geometry of responses has clarified in some cases what symmetry tells us. But the first example of this, I mentioned the date 1980 already. If you do a very standard semiconductor experiment on two-dimensional electrons at moderately low temperature and moderately high magnetic field, something interesting happens. And very quickly, the interesting thing is, normally when you do this measurement, which is run a current along one direction and measure the voltage that builds up transverse to it, the current gets bent by the magnetic field and you get a sort of straight line dependence in the Hall resistivity, the red curve here, with magnetic fields. So that straight line dependence you can see at weak fields here. But as I increase the magnetic field, I get these flat regions. And those flat regions, they have the remarkable property that the Hall conductance on one of those is an integer times e squared over h to about 1 part in a billion. And you note that's e squared over h. It doesn't really care about the specific material. This is what I mean by universality. And I'll review how that happens, because there's been about a systematic, I would say almost a 40-year systematic process of generalizing this idea to many, many other things in solids, now including metals. And I want to sketch how that program works, at least in one way of looking at it. And then this note 2 at the bottom is the thing I'll come back to at the end of this talk is there are actually additional plateaus if you make the sample very clean, which correspond to rational fractions of E squared over H, like P over Q times E squared over H. Maybe the first one is at 1/3 E squared over H. And those, believe it or not, come from fractional particles with fractional statistics. And I'll say what that means later on and how we're looking for other examples of that in magnetic systems. But first, where does this come from? And I will give maybe not the first picture, but the one due to Thouless that won, at least contributed to his Nobel Prize fairly recently. Because this Berry phase picture that started with Thouless and collaborators turns out to, first of all, show very nice connections with gauge theories in particle physics, and second, to be applicable to a whole bunch of other things. And also it naturally maybe helps you figure out, once you've got a topological phase in the sense of some topological invariant of the wave functions, what kind of electromagnetic response does that give you? So I'm not going to try to cover these examples today. I'm going to tell you about the two-dimensional quantum Hall effect, which was maybe the original case. And then I'm going to give one example of the three-dimensional Z2 topological insulator, because that's a neat case where actually the particle physicists had sort of figured out a lot about this phase without really knowing what they were talking about, but they did have the right effective theory for something, and then condensed matter physicists figured out what the something was. So the neat thing about this Berry phase approach is we're going to introduce some gauge fields that live in the Brillouin zone of a crystal. And those gauge fields, it turns out that when we can make gauge invariant objects out of them, which is something we learn to do as theoretical physicists, then pretty much every gauge invariant object we can make has some physical meaning. And as a result, even if you don't care very much about topological phases, if you just care about measurable properties of electrons, these Berry phase objects are fairly useful for things like electrical polarization, magnetoelectric effect, and so on. And then one of the frontiers, there's still a few frontiers left in this analysis of nearly free electrons, say, but one of them is, how is this all relevant to the physics of metals? And that's what I'm going to focus on once I finish up the intro. All right, so the idea of this gauge field in the Brillouin zone, let me first just make a general statement about quantum mechanics, which you might well have heard, but just in case you haven't, let's say that the Adiabatic Theorem you learned in quantum mechanics is only part of the story. So the Adiabatic Theorem says, if I've got a non-degenerate state of a Hamiltonian, and I change the Hamiltonian slowly and don't close the gap, then I will remain in that state effectively, or the adiabatic evolution of the state I started in. There will not be transitions. But it turns out that there is a phase I build up. There are different phases I build up, but there's one which is particularly interesting because it's just geometric in the following sense. Often our Hamiltonian depends on some parameters. And for us, in a moment, the parameter is going to be momentum. If I take the Hamiltonian around a loop in parameter space, I can build up a phase. And that phase I build up, I can actually write it as an integral of a vector potential. And that vector potential lives in parameter space. And I make it out of wave functions in the following way. So the right equation, what I'm doing there is saying, okay, I've got a non-degenerate state, which means one wave function at each point of the Brillouin zone, at each point of parameter space. And I can look at how that varies with parameter and try to define some object. And I'm going to claim to you in a second that that object is very, very similar to the vector potential in electromagnetism. It's a U1 gauge field. And the way to understand that is maybe to think about, if you and I chose different wave functions, would we agree on this A, first of all, and would we agree on physics? Well, we should agree on physics because the overall phase of a wave function is sort of a choice. And in this case, that's the only freedom because I said I had a non-degenerate state. So what happens if you and I choose different phases for the wave function? Well, let's assume for simplicity that we differ by some smooth choice of phase. Then if I choose psi and you choose this other version, what happens to A, which is the Berry vector potential or Berry connection? And the answer is that A gets shifted by the gradient of phase, which ought to look familiar because that's how the vector potential changes in E and M. So now we're in business because that tells us that A itself can't be physical because it shifts by this arbitrary phase factor or gradient of a phase factor. But we know how to make objects out of it that could be physical. So for example, the curl of A doesn't have that dependence, and the curl of A the Berry curvature is the simplest and still probably the most important version of this. And an object that comes up actually in the three-dimensional topological insulator, one reason I thought I might mention it briefly is, but very briefly, unfortunately, this non-abelian part, if I've got two different bands, say, like if I've got multiple degenerate bands, or often if I've got many occupied bands, their energy differences don't matter, so this object is still important, then I can just add band indices to the wave functions and I get a non-abelian connection, like what you would see in quantum chromodynamics or something. But again, you need to think about what are possibly physical gauge invariant objects you could make out of that. So the first example of the usefulness of this Berry curvature object, actually, that may be an overstatement because it turns out people had sort of thought about it in metals even earlier, but they didn't know it was a Berry phase because Berry hadn't done his sort of unifying work. And again, you know, Berry, it's probably important to say that Berry did not invent the Berry phase in the sense there were physical examples before. The Pontryagin phase in optics is probably the most famous. But he kind of unified, I guess, the ideas from many different areas of physics and realized these are all examples of one thing. So the case that's relevant here was if you try to calculate what is the Hall conductance of a two-dimensional material. So Laughlin had already given an argument a year or two earlier why you get quantization in the integer Hall effect, but it wasn't really standard transport. It was this idea of pumping. So what Thouless and collaborators set out to do was, let's just calculate in the standard way, what is the conductivity? Because normally you don't get quantized conductivities and things like that. But with a bit of massaging, they got this formula at the bottom, which is saying that the contribution of a band to the conductivity is an integral over the Brillouin zone of some object. And that object is just the Berry curvature. So in other words, this thing in parentheses is just F. And the integral of the curvature over a band turns out always to be an integer. In the right units. It's a Chern number or TKNN integer. But basically this says that every band of a two-dimensional crystal, you can assign a number, a topological index. And if the band is occupied, then it contributes that index to the Hall effect. And that gives you an idea for why these things might be quantized when you go out and measure them. So now here's a more fancy example. This is my last example of insulators before we move on to metals. But this is the case I meant where, actually I think the one time before when I was at IISc, I mostly talked about this, so I will be quick, and I'm sorry for those of you who heard it a few years ago. The idea that people like Wilczek had back when the axion was first being thought about, the axion was a particle that would couple to E dot B. So what if you just think about, could there be E dot B couplings in the effective electromagnetic Lagrangian of some solid? It had better be an insulator for you to measure this. So Wilczek's point, and this sounds crazy, but I'll try to give a picture of it in one slide, although it'll be going by a little bit fast, but you can certainly read more about it, was that actually in the right units, the coefficient of E dot B is an angle. And in that sense, E dot B is very special in a number of ways. It's different from E cross B or other bilinears. If you just looked at E dot B from a symmetry point of view, you would think you have to break both inversion and time reversal to allow this. It turns out that you don't. If you have inversion or time reversal, then, or both, that actually means that theta has to be equal to minus theta. But once you realize that theta is an angle, which was Wilczek's point, and how to translate that to condensed matter, I guess, it means that there are two possibilities because the angle 0 is equal to minus 0, but pi is equal to minus pi. The second thing that's special about E dot B, if you write it out in terms of the field strength tensor, it turns out that it's a total derivative of ADA. ADA is the so-called electromagnetic Chern-Simons term, but the fact it's a total derivative means that, in a sense, even though this looks like a bulk effect, you can move it to the surface of your solid. And what that means, I'll tell you in a second, but it was kind of a surprise that as of 87 or so, there seemed to be two kinds of time reversal invariant insulators. There would be theta equal to 0 insulators and theta equal to pi insulators. And whenever you had a boundary between them, it turns out you would have a funny kind of Hall effect. So the three-dimensional topological insulator from condensed matter got going around 2006. Several groups realized that there were two kinds of insulators. One of them had an even number of Dirac cone surface states, even number usually 0, and the other always had an odd number. And the odd number is what we call the 3D topological insulator. But it turns out that these two ways of finding two kinds of insulators are actually the same. In other words, we think of an odd number of Dirac cones at the surface as being theta equal to pi. The way that kind of connects together is to imagine if you slightly gapped the surface, if you added a magnetic field, say, that was weak enough that didn't really modify the bulk, but it just modified the surface, you would get a Hall effect at the surface, and that gives you an E dot B term, because I told you that E dot B in bulk is like something at the surface. It turns out it's like Hall effect at the surface, and you can picture that. If you apply an electric field, you'll get current circulating around the surface, and that gives you your magnetic moment. That's the E dot B effect in surface terms. And then the difference between a theta equal to 0 material and a theta equal to pi material is just that a theta equal to 0 material, like an ordinary insulator, has an integer Hall effect at its surfaces, while a theta equal to pi material has a half integer Hall effect at its surfaces. So you can get a lot of things out of this picture and push it through in gory detail. And I have given talks on that, but I don't think this is the one. But maybe the one thing that might be interesting to people from another area of physics is that this leads you to a new way to write down the Z2 invariant. It turns out that it's a topological invariant that comes from the non-abelian Berry curvature of the bands in the solid, specifically the Chern-Simons form of the non-abelian part of the Berry curvature. So I think that was the first physical appearance of the non-abelian part of the Berry curvature of bands. So that's what I wanted to say about insulators as kind of a warm-up. And we keep finding new examples. Maybe the hot new example in the last year or two is manganese bismuth telluride seems to be an anti-ferromagnetic topological insulator. And in other words, you even if you don't have time reversal, you can have a combination of time reversal and lattice symmetry. But there are other possibilities, and work on insulators keeps going. I want to talk about metals and how metals, in a sense, were the first playground for Berry phase effects. But how, if you took the old ones, you would be pessimistic about what metals could give you at maybe a quantized or clean level, and how semimetals come to the rescue. So first, I want to explain why the Berry phase, if you're teaching an undergrad class or something, maybe, I guess you all probably don't have to worry about that as much as I do. The Berry phase is actually more fundamental for metals, I would say, than it is for insulators. And one reason is to ask, what does the Berry phase control, or what is its physical meaning at the simplest level? And that goes back to, well, I think the simplest thing that directly is expressible in terms of A in an insulator is the electrical polarization. That winds up being the loop integral of A, the Berry connection. And the electrical polarization, we know that has to have something to do with the electron spatial location. Like if I moved all the electrons over, I would change the polarization of the crystal. And that's a clue for where maybe the Berry connection should show up in the basic theory of solids. And so in other words, polarization, even though people had tried to compute the polarization of solids for at least 50 years, they never quite got it right because they didn't have the Berry phase. And then around the late 80s, they finally figured out how to do it correctly. So maybe the deeper reason why something like the Berry phase was necessary, at least something related to the wave function, is that if I just look at energy bands, E of k, energy bands are symmetric under k goes to minus k just from time reversal, even if I break inversion. In other words, if I take a non-magnetic material with broken inversion, that's most of the ferroelectric materials, the sort of polarized materials. I wouldn't be able to stare at the band structure and tell that it had broken inversion. I need something about the wave function. And the easiest thing about the wave function is the Berry phase. Not the only thing. I'll give you another example later on, but there have to be some wave function dependent properties, not just E of k, in order to tell that you broke inversion, basically. So how that shows up in solids is what's sometimes described as the biggest omission in classic books like Ashcroft and Merman, which is that if you look at how a wave packet moves in a solid, in a metal, there's one term which is there, which is the group velocity. And then the second term is called the anomalous velocity. It was really introduced by Karplus and Luttinger quite a while ago, but they didn't really have this Berry phase picture. But what appears here is the same F Berry curvature I talked about before. And the way to think about why this term is there is that it's like a change in polarization gives me a current. In other words, think of F as like dA by dk, and A is like the polarization. This is like the total derivative of polarization in time, so it makes sense that's a current. If you want a more microscopic picture, the standard group velocity is a velocity that even a point particle would have. But the anomalous velocity is because the electron wave function has some distribution in the unit cell, and that could be changing when the Bloch momentum is changing. In other words, maybe at one momentum, the electron is sitting on atom A, and at a different momentum, its wave function is sitting on atom B. Then if the momentum is changing, the electron will kind of shift from atom A to atom B, and that's an extra current, like a current within the unit cell. And Karplus and Luttinger were thinking about this because they thought there must be some extra contribution to the current in original measurements of the Hall effect by people like Hall in magnetic metals like iron. So I'll recap that and then talk about examples that are more relevant to optics. But from the original case, the Hall effect, the so-called intrinsic Hall effect from Berry curvature, you might worry that this was not likely to give you anything quantized. But the way that goes is, I told you before that sigma xy in an insulator has a piece which is the integral of Berry curvature. So it turns out that there is still a piece, even in a magnetic metal, which is the integral of Berry curvature, except that now it's only over the Fermi sea. And you can rewrite this in various ways, but let me stick with this way. There are also other pieces that are more like what we're used to. They're like scattering at the Fermi surface. And in fact, if you want to know when is this intrinsic term, the Berry curvature term, dominant, it's basically dominant in metals that are not too clean and not too dirty. And it's hard to do very controlled calculations to find a limit where this is dominant. That's one reason why this is a very hard problem, but I think it's now accepted based on experiments say that in many magnetic metals, there is a big range of conductivities where the dominant sigma xy is this term. However, now the integral of the Berry curvature over the full torus, which is a closed manifold, like in an insulator, will be quantized. If I'm only integrating over part of it, over the Fermi sea, then there's no real reason for it to be quantized. And in general, it won't be quantized. So this gives you an effect that is physical and important and all that, but it's not quantized like it is in insulators, basically because the Fermi surface is a continuously changeable object. But that's a clue that if you wanted something that was quantized, maybe you should have a special Fermi surface that isn't continuously changeable in the same way, like a Dirac point or something. But before we come to that, let me tell you about an effect that we studied in 2010, not realizing how interesting it was. We were interested in it just as another way to measure the Berry phase that might be a little bit cleaner in some sense than those Hall effect measurements. And the idea, it's called the circular Photogalvanic effect, and it's basically a photocurrent, so a current induced by light, which is a nonlinear effect, order e squared, if it's proportional to the intensity. So a current that will change direction depending on whether the light you shine on your sample is right circular polarized or left circular polarized. So the way that this works, suppose I just think about semi-classical theory of electrons, and I push the electrons to the right, and I'm at low frequency, so they reach roughly equilibrium. So their distribution has moved from the black circle to the gray circle. So then, because the light is circularly polarized, the gray circle slowly moves around in a circle. The ordinary velocity will certainly average to 0, but it turns out that in the right crystals, the anomalous velocity, that Berry phase term, will not average to 0. So we think that there's a long history of experiments on this circular Photogalvanic effect or chiral photocurrent that we're measuring the Berry phase, but they're not in ordinary samples. It's not particularly quantized. It's a very weak effect. The magnitude is consistent with predictions of this theory, but then we sort of gave up for 7 years or so. It seemed like it was a Berry phase effect, but quite weak in general. We went on to other things, but now to kind of explain what happened in those 7 years, one of the things that happened was the discovery of some very interesting new materials. So basically, if you go back to the early days of quantum mechanics, right after Dirac came up with the Dirac equation, which is a 4x4 matrix equation, two people figured out two different ways to sort of cut that equation in half or break it up into 2x2 pieces. One was Weyl and one was Majorana. And those two ways are two of the hotter topics in condensed matter physics the last few years. So the one for today is what Weyl did, which was If you had a massless particle, then its helicity is fixed, because if it's massless, you can't boost to a frame moving faster than it to flip its helicity, basically. So in other words, left and right-handed fermions sort of decouple. So that seems to exist in several solids, and the reference material, the standard example, is probably tantalum arsenide. That was the first one discovered, I think. And in our condensed matter language, we would just call this a two-band semimetal, where there's a band crossing somewhere in the vicinity of the Fermi level. And people had sort of been looking for those things off and on until, at least going back to the PhD thesis of Conyers Herring around 1935 or so. So it's great that they were finally discovered. So what good is that, is the next question. Well, first, one thing that happened since the Herring days was people realized that there is a topological significance to these vowel points, these two-band crossings. And that is, you can assign a charge to these vowel points. Basically, if I make a little sphere around one of these points, they are magnetic monopoles of Berry flux. Just like you might expect, it turns out they come in pairs, or even if they don't come in pairs, the total charge has to be zero. That's the Nielsen-Ninomiya theorem applied to condensed matter. But there is still a consequence of this topological idea, which was really important in the experimental discovery of these Weyl semimetals, which is, if you go to the surface, they're somewhat like three-dimensional topological insulators in that the surface state is half of what you might expect. In a topological insulator, 3D topological insulator, the surface state has an odd number of sheets of the Fermi surface, when normally time reversal forces you to have an even number. In a Weyl semimetal, you get a Fermi arc, which basically means that half of the Fermi surface, just one half of the K points, could be at the top of a slab, and it's kind of continued at the bottom surface of the slab. And that's a very strange thing, to have a Fermi arc instead of a closed Fermi surface. And one neat prediction for that, which is seen in experiments by my colleague James Anlidis, is it means that a quantum oscillation orbit could start on the Fermi arc in the top, and then in principle penetrate through the bulk to the Fermi arc on the bottom surface, and then come back. So you get sort of a macroscopic quantum oscillation orbit. So anyway, there are various surface signatures that were the key to finding maybe that Weyl semimetals exist. But what about bulk? Now that you've got Weyl fermions, there must be something interesting that they do. And in particular, is there something like this graphene example I mentioned? Well, yes, but it takes a while to get there. So the first thing that people started thinking about right away was the chiral anomaly, which is a neat effect. If you had a single Weyl fermion and you applied parallel electric and magnetic fields, single charge Weyl fermion, you would find something odd, which is that charge doesn't appear to be conserved anymore. So we don't expect that in solids, which is why it's good that for us, the total charge of the Weyl points is zero. That means that if you could apply both electric and magnetic fields, you sort of pump charge from, say, the negatively charged Weyl points to the positively charged ones. And it's an order quadratic in the E and B fields. But that sort of motivates looking for interesting effects at second order in E and B fields. And the one I mentioned I'm going to focus on is actually 2 powers of electric field, because it's been hard to do experiments clearly seeing 1 power of electric field and 1 power of magnetic field. You sometimes get higher powers, and I'm not totally sure that we understand everything in the magnetotransport measurements. So there is a story that I think in the interest of time, I'm going to skip over about why can't you just do some linear effect? It turns out you can calculate the linear response that people had hoped for. It winds up being quite interesting, and there's a very simple universal formula. It's kind of neat that what appears in the universal formula is the magnetic moment of a Bloch electron. But I guess what I would say, and I'd be happy to say more about this if people ask me at the end, is the idea of a chiral magnetic effect, just applying a magnetic field, even an oscillating magnetic field or something, and seeing something unique has sort of gone away. You can see optical rotation, but optical rotation is there even in old-fashioned materials that have nothing to do with Weylness. You just need some low symmetry. The one neat fact maybe for condensed matter theorists in the audience is that it reveals, or this is an application of another way that maybe Ashcroft and Merman's semi-classical equation is a little bit incomplete. If you look at even the group velocity term, then once you apply a magnetic field, you have to be a little bit careful because there's an extra energy, which is this kind of Zeeman energy term. This m sub nk is the orbital magnetic moment of the Bloch electron. And the orbital magnetic moment of the electron is a lot like the Berry curvature. In fact, it's so close that when we first started computing with two-band models, we got confused. But basically, it's the Berry curvature with an extra power of energy sandwiched in the middle. But it has a nice physical meaning. It's the orbital magnetic moment. It contributes to the group velocity, and that resolves all the sort of paradoxes about the linear effect. So that's all I have to say about the linear effect. All right, so on to the quadratic effects. And this is the sort of optimistic, just experimental fact I mentioned before, which is if you try to measure nonlinear optics on Weyl semimetals, this is work originally by my colleague Joe Ornstein, now seen by other groups as well, their intrinsic nonlinearity in typical frequency ranges like 0.8 eV is stronger than any other known material, stronger by a factor of 10 or so. So in other words, you put in light at omega and you get out quite a large amount at 2 omega. The reason why this is not immediately useful for technology is that these are semimetals, which means they're a little bit lossy. It is slightly useful, at least for sort of physics lab technology as a quick frequency doubler, if you don't want to phase match or things like that. But I don't think it's going to lead to a big startup or something, but it is neat that it's a very large second order effect. It encourages maybe to think that other second order optical effects might be practical in these materials. And now comes the fun, because then you can think about, well, what are other second order optical effects that might be interesting? And the one that we wound up converging on is actually the same effect that we studied in 2010, but now in a Weyl semimetal, where something interesting becomes possible. So in particular, if you take a Weyl semimetal of low symmetry, you can separate the positive and negative Weyl points in energy. In other words, the Nielsen-Ninomiya theorem says your overall charge has to be 0, but that's overall over all the energies in the crystal. It doesn't mean that they can't be at different energies, which means you could put the Fermi level, mu, at an energy where you filled up, say, one Weyl point, but not quite the other. Now you applied light. Light generates transitions, energy h bar omega. You can get transitions across the Weyl point on the left, but you don't get transitions across the Weyl point on the right. They're so-called polyblock because the final state is filled. You'll still get sort of semi-classical effects on the right, but those are the ones we computed in 2010, and we knew they're really small. So now you go back, you can't do it semi-classically anymore. You actually have to compute optical transitions, but there's room for something neat to happen, because just the way topology works is often that you start off just ordinary perturbation theory, initial states and final states, and you realize that there's something more to the story. And here, the something more to the story is that the initial and final states for this transition on the left know that there's a Weyl point in the middle, because I couldn't get rid of the Weyl point locally. That's what it means to say that it's got a topological charge. So I can study the standard optical transitions. I've got the lower states and the upper states. I do my perturbation theory, and you get a result that actually all the microscopic features kind of drop out. So that's this formula at the top of the line, and the top of this slide. And I'll show a little bit about materials and data in a second, but let me focus on the theory part. So by power counting, you could already tell that if you were going to have an extra power of electric field, you would need to inject a three-dimensional current density. In other words, you need a dj dt, and j is three-dimensional. So what this is saying is that the difference between right circular and left circular current injection is e cubed over h squared with some fundamental constants times intensity times the Weyl charge. So that's the effect from the Weyl point, and then there are effects from the other bands that were polyblocked as well, but those are small. So this is at best, 1% quantization. It's probably more like quantization within 20 or 30%. But the point is the natural scale is e cubed over h squared. And in particular, even measuring magnitude turns out to be a little bit difficult in this kind of experiment, but the main maybe qualitative prediction is that you should get a contribution from one Weyl point that is large compared to anything non-Weyl, and then it should be canceled out once you hit the frequencies where you get transitions across the other Weyl point. So the basic idea, and it's nice when theory comes before experiment, and I can say that because the bottom theory paper I'm not on, it has a lot of friends of mine, but they sort of implemented this idea for a particular material discovered by Zahid Hassan's group, rhodium silicide, and said, look, you should see a plateau corresponding to the quantized value for frequencies up to about 0.7 electron volt. 0.7 electron volt is where you should get, it's where you should start to allow transitions across the other val point, and then you should basically drive the effect down to nearly zero. Then it becomes a matter of making the sample and trying to do the optical experiment. I'm not going to say too much more. I mean, there are ways to understand the value of this quantum, if you've ever thought about graphene or something like that, that are not very mysterious. Maybe the simplest way is just to sit down and do perturbation theory, write down your optical matrix elements, and realize that you can transform away frequency. It's very much like what Thouless et al. Did. You start with something that is ordinary perturbation theory with energy denominators, and you realize that there's a cancellation between the numerator and the denominator. So this is just saying whatever your favorite simple way is of calculating optical response, you can apply it to the val point and you will get the same answer. It's just one electron physics and perturbation theory. So the experiment is done all optically. You shine in a pulse of light that creates these transitions, which result in a little burst of current into the sample. And then you measure the terahertz radiation, the low frequency radiation from that burst of current. And you look to see, does it look like what you were hoping for? And the answer is more or less yes. It's not a perfectly flat plateau. This is where the laser kind of pukes out. But there is at least a range, and you know, there are band structure corrections, disorder corrections, and so on. I have a slide or two on interaction corrections, but basically, you do have something like a plateau, then you hit the frequency where the other val point becomes activated, and this drops nearly to zero. So that's just published last year. And we take it as at least indicating that this is an optical effect that comes from one val point and is canceled by the other. The magnitude, I do not think, is reliably measured in this experiment, but there are claims by later groups that I haven't had time to form an opinion on myself, saying that they do measure a magnitude which is maybe consistent with the theoretical prediction. So there are interaction effects in addition to the band structure effects I mentioned.
Sure. I just had a quick question about your last slide. Once it starts dropping, what controls this energy scale at which it drops? Is there an energy?
Yeah, I think the simplest one, and there's actually some neat work. Yeah, okay. This is not a particularly clean sample. So I suspect that it's largely disorder broadening is a large effect here. So, and let me maybe make one other reason that now that I've mentioned disorder, I can also say why the magnitude is difficult to measure a quantized value if you have at least a dirty sample. So this is saying what's quantized is not really the current, it's the rate at which current increases from zero. So unless you have a very clean sample, you'll eventually reach an equilibrium where you're increasing current, but then current is relaxing. Like in a relaxation time picture, you'd have a minus J over tau, and you'd reach a balance between creating current and relaxing current. And that's certainly what's happening in this rhodium silicide sample. So to estimate the magnitude, you need to make an estimate of tau, and that has enough uncertainty that you can't get the magnitude very well. So the key to getting a really quantized measurement is to make it clean enough that you're still in this ramping up phase. You haven't reached equilibrium with the scattering. So anyway, I guess I think that the width here is probably indicating that the scattering time in this material is not particularly long. So in other words, I think that if you made a cleaner and cleaner material, you would get a sharper and sharper drop.
Okay, thanks.
Hi, sorry, Jules, the small clarification. Does it depend on the surface on which you do this experiment?
Let's see. So there are additional sometimes contributions from surface states, but for the bulk effect, I don't think, okay, so let me maybe back up a moment. What's actually quantized is down here on the bottom. It's really the trace of this response tensor, which is kind of a sum of components. So that I don't have, I can't, okay, I think the answer is there are surface optical effects that do depend on the surface. I think if you can, what we're really trying to measure is this trace of three components of the nonlinear response tensor. And if you can measure that on any surface, you should get the same thing. And I don't remember, I think they wrote a subsequent paper that's about surface effects, but I'm afraid I don't remember enough of the story to give you the answer.
Sorry, another clarification. Can you repeat what decides 0.7 EV? I missed it. If you have a different doping, if you have a different doping.
0.7 EV is just the difference between the positive and negative Val points in rhodium silicide, basically. So rhodium silicide is an interesting material. It has a sort of multifold, a highly degenerate Val point, and then it's some higher energy. Let's say that's got like a charge of +4. At some high energy, it's got a combination of -4 Val charges that cancel it out. So if you want 0.7 is the energy between, in the band structure, between the center of the left Val point here and the center of the right Val point. So it's where you expect to start generating optical transitions across the other one.
Okay, so it does not happen in tantalum arsenide.
That's right. Tantalum arsenide actually has, it's not chiral. So tantalum arsenide has a lot of Val points, but the positive and negative are at the same energy.
Okay, fine.
So in fact, yeah, the reason why, I mean, we had a different candidate material. To give credit to Zahid, what was special about rhodium silicide was exactly that it has this large gap between the positive and negative points. Most of the other materials, either that gap is 0 because of symmetry, or else it's small.
Okay, thank you. Thank you.
Yeah, so and yeah, so there are interaction corrections, and one little story. They're not particularly.
So can I ask a question, please? This is Krishnendu. So, is there a particular symmetry in this compound which is broken to have this gap between the positive and the negative? This thing.
Yeah, basically, it has to be chiral, so no mirror symmetries. That's what makes it special. So tantalum arsenide, for example, it breaks inversion, but it has a lot of mirrors. While rhodium silicide, not just does it break inversion, but it has no mirror symmetries, which both allows chirality in linear optics, but also allows the energy splitting of plus and minus.
Okay, thanks.
Yeah, I think there is another, there's a cobalt-based chiral Val semimetal that I think Liang Wu has published on. So there are at least a couple in this category, but yeah, definitely the standard tantalum arsenide, tantalum phosphide, and so on, the sort of standard family of Vals have a lot of mirror symmetries. They are very strongly inversion breaking, but not breaking enough of other symmetries to separate an energy of the Val points, yeah. So yeah, the point of this slide is you can compute interaction effects and find that they are present. There's some frequency dependent vertex correction that matters. And it's not even all that small. Basically, the natural scale of it is the fine structure constant in the material. So in other words, it's like dependent upon the velocity of the Val point, and that velocity is a lot less than the speed of light. In graphene, it turns out that this correction is small for sort of accidental reasons, as far as I can tell. It turns out that in graphene, the vertex correction would spoil the quantization a little bit, but the coefficient of it is 19 minus 6 pi over 12. In graphene, it just winds up a number that would normally be of order unity is 1%. Maybe there's some deep reason why it's so small in graphene, but I don't know it. In our case, it's not particularly small. So we think that there are interaction and band structure corrections, but at least they're corrections to a magic number, which is E cubed over H squared. So that's kind of the punchline of the main part of the talk. And I might just take 5 minutes, I guess, to wrap up. So the story of quantization in solids at the 1 electron level, you could categorize things by how many powers of electric charge they have. So we know about the flux quantization and things related to it have 1 power. That gives you the Josephson frequency, for example. There are a lot of examples that order E squared over H. Even the 3D topological insulator has things related to E squared over H. Graphene optical transmission, you should really think about it E squared over HC maybe. But as far as I know, this is the first example where you get E cubed over H squared. Again, with a lot of caveats that, I wouldn't think of this as like a quantized value you could use for metrology. It's more like a natural scale, but it's saying that the natural scale for the circular photogalvanic effect in Val semimetals is E cubed over H squared because of the way that optical transitions work across a Val point. So that was all, you know, in some sense, one electron physics. And there we know what we're doing on several levels. So when it comes to fractional phases, which are at least as interesting, fractional phases, it's harder to find examples, and it's depended more on experimental luck. But I did want to close with a bit of optimism, even on the fractional side of things, which is that just in the last year or two, classical and quantum computing have made more progress on predicting fractional topological phases like spin liquids. And experiments might be getting a little bit better too. So it's becoming, I guess, a little bit more of a systematic search. And the example I thought I would give really goes back to Anderson. But briefly, for I think most people will have heard this in this particular audience, but basically, in addition to the integer topological phases, where you normally look for quantization of a response as the magic, there's an even deeper fact in some topological phases, which is that the electron breaks up. Say you can get 1/3 of the electron charge and statistics that are neither bosonic nor fermionic. That happens in Laughlin's theory of the fractional quantum Hall effect. It turns out that you might have heard that people want to use these states to build quantum computers. That continues, although it's hard. For the first time, people are starting to use ordinary quantum computers, not topological, just superconducting qubit machines to make these fractional states. And I'll flash up a reference at the end. But before I come to that, let me just explain, you know, where this field is still hard after many years of trying. Probably the simplest example of a hard problem is the Heisenberg model on the Kagame lattice. This is the Kagame lattice. The Heisenberg model is just an antiferromagnet of spin half degrees of freedom that want to form singlets, basically. And even after all these years, very many smart people disagree on what is the ground state of this Hamiltonian on this two-dimensional lattice. And I cannot tell you a solution for that today, but even before the Kagame, there's another spin liquid that people thought about. Actually, the original one that Anderson thought about starting in 1973. And it turns out that it's not quite the spin liquid that Anderson was thinking about, but at least the model he was thinking about, we think does have a kind of spin liquid, and we have sort of new ways to understand why, maybe. But it is true that maybe to really prove that is going to take either experiment or a real advance in computing, maybe from these new quantum computers. So if you're wondering, where does something like this Heisenberg Hamiltonian come from? Remember, it comes from a Mott insulator. In other words, I've got electrons that are repelling each other, so I've got one electron per site. It turns out that as I start to let the electrons hop around more, I get additional interactions beyond just the nearest neighbor J. But if I'm deep in a Mott insulator, then the Hamiltonian is this Heisenberg one. When I get close to the Mott insulator transition, I get extra interactions, which are actually going to be the hero of my mini story. And the model that Anderson thought about was just the triangular lattice, this very simple lattice, and the Hubbard model. And it turns out that we know that deep in the Mott insulator on the triangular lattice, Anderson was not quite right. And the state you get is just a conventional state with 3 sublattice order. In other words, there are 3 sublattices on the triangular lattice, and you could have 3 spin directions for those at 120-degree angles. It turns out that when you get closer to the Mott transition, we had a numerical observation from a couple of years ago. It took a very long time to get published, I will say that, because it was numerics and we didn't understand a reason maybe, but we at least had a lot of ways to characterize it, that what we were seeing close to the Mott insulator was a so-called chiral spin liquid. It was basically the spin version of the fractional quantum Hall effect, which is a time reversal breaking state. So in other words, it spontaneously breaks time reversal symmetry and chiral symmetry, and then it forms a topological state, which, just like the quantum Hall effect, has edge states and things like that. So what I wanted to report on now is maybe why we think that happens. But first, you know, because I'm wrapping up and it's a colloquium, it's important to be honest that, first of all, just because you find one of these states in one particular Hamiltonian, you know, nature, I'll show you, has a million different possible states that are very close in energy, and there are a million different compounds that all have slightly different spin Hamiltonians. So it's a very, there's a real zoo of possibilities. For the triangular lattice, there are probably 3 states that people talked about the most, which you could think of as the Z2 spin liquid, the sort of gapped time reversal symmetric state. The chiral spin liquid is a gapped but time reversal breaking state. And one way to tell it apart is that it has a sort of gapless state running around the edge, which the Z2 spin liquid doesn't. And what we were actually expecting to find, because it's been popular in recent years, is a gapless spin liquid on the triangular lattice. So, and yeah, this is my plug. We actually wrote a book that just came out this summer, Roderick and I. Roderick is another friend of ICTS. And there, so if none of this is making sense to you, then we did try to explain it at a more basic level finally. So the basic reason why we think the chiral spin liquid happens is that if you take all the terms that get generated systematically close to the Mott transition, at least the first set, you can rewrite them in terms of the chirality and see that they favor chirality breaking. Once you have chirality breaking, it's kind of natural to get the chiral spin liquid. And there's a whole story, but since I didn't want to talk about that really, I wanted to talk about many other things that could happen. So these are the various conventional and spin liquid ordered phases. So we're betting on the chiral spin liquid in the Hubbard model, but you know, the challenge is it's likely to remain very hard to settle this with classical computation. So some people agree with us. I'm not sure that everyone yet does. And even if people agree with us, you know, you could change the Hamiltonian slightly, and then you basically have to redo the calculation, and it would take a whole lot more computer hours and so on. So this is an example of where maybe the field is, we know many possibilities, and trying to connect actual materials and Hamiltonians with the possibilities is one of the frontiers. But at least in this case, we have sort of a physical energetic picture of why the chiral spin liquid is favored. And that was in our 2021 paper. So that's our breaking news. Since the experiment I talked about before was from last year, I thought I should put something new in the talk. But maybe the breaking news that more people might care about is that, first of all, the experimental situation was just kind of thrown into disarray by the science paper, because the experiments on at least one triangular lattice compound seemed to suggest that it was gapless. And now there's an experiment that sees a gap. They didn't really look for time reversal breaking, but they didn't see a finite temperature phase transition. So I wouldn't necessarily present this as supporting our state, but for the people out there thinking about magnetism, it seems like, you know, the triangular lattice, there are still a lot of possibilities out there. We just posted a paper on a different compound that's triangular lattice, but that one seems to be close to critical. So at least there are some signatures, but we're still kind of at the stage of many different possible answers, and you have to do experiments to know which one applies in a particular compound. And we can, with a lot of work, maybe understand particular models. But you know, what new is happening? So that's, you know, in some general sense, it's not that different from where we were a few years ago. So what I thought was a reason for optimism is that, first of all, a lot of people with these new gate-based quantum computers are suddenly very interested in quantum magnetism and topological states and things like that, because they're easier in a sense than factoring large integers. So I'll show you in a minute papers by Google and Microsoft and so on. But basically, it looks like being able to calculate spin liquids, and in particular, neutron scattering of spin liquids, and this is a Department of Energy report that sort of reached this conclusion a couple of years ago. All of a sudden, you know, our problems of quantum magnetism, because they have well-characterized Hamiltonians and because they have high-quality data from neutron scattering, all of a sudden they're kind of emerging as test problems for quantum computers. As an example of that, it's rare to see a condensed matter paper with 100 authors, but there is one on the archive, which is about using a quantum computer to demonstrate braiding of quasi-particles in the toric code. And there are more and more simulations on quantum hardware coming out now of basically the same kind of spin liquid Hamiltonian that I talked about. But so far, they're mostly reproductions of known physics, I would say. So we're starting to have quantum computers that are beyond what we can do classically, but they haven't yet demonstrated so-called quantum advantage, at least on any problem that physicists care about. But I do think it's no longer easy to just rule this out and say that quantum computing will never teach us anything useful. So we've just started doing this kind of quantum calculation as well. And so far it's pretty noisy, but there is at least a pathway that some of these quantum matter problems that many of us care about are going to be about the first science problems solved on noisy intermediate scale quantum hardware. And that's where our experiment and theory have kind of a new life, as trying to be guides for that process. I mean, I sort of like what we do anyway, but this is maybe yet another reason to do it. So I thought I would end on that optimistic note. So thank you all. I wanted to say that, you know, there really were two parts to this talk. So the first one is one electron. We have kind of a general set of concepts and a strategy, and we keep finding new examples where that strategy works, and it's very satisfying. Fractional topological phases are more wild, and there's a zoo out there, and we need to find what we can. There are successes, but it remains difficult to do really predictive science. I think it is possible in the fractional quantum Hall case, but for spin liquids and things like that, it's very hard to say that this given chemical formula will produce a Z2 spin liquid or something like that. If we could do that, we'd probably have better experimental examples than we do now. But one thing that's kind of exciting from a quantum matter point of view is that all of a sudden there's a whole new crowd of people that care a lot about what we do and are trying to understand the same kind of states that we're trying to understand. So I thought I'd close with that. So thanks again.
Thank you, Joel, for the nice talk. So the talk is now open to questions. So I think one way to go about this would be you can raise your hand and then I can try to call up names and you can unmute yourself and ask questions. So the first hand I see is of Ajay Sood. So you can unmute yourself and ask a question.
Hi, Joe. A very exciting talk. Congratulations. My question is on the last part on this chiral spin liquid. The gaps one are the ones which you talked about for Herbert-Smithite or the ungapped? I missed that point.
Yeah, so the Herbert-Smithite, I don't really have anything much to say. The main experimental material is this complicated organic. And there is now believed to be a gap. So the story of this material, Kanoda, one of the authors of this paper, had an experiment about 10 years ago that was the best sign of gapless spin-ons because it showed a thermal conductivity that looked like fermions in an electrical insulator. So it was taken as a sign of spin-on thermal conductivity in this material, but now it turns out that better samples seem to show a gap in the spin sector. So their interpretation is actually that it's a valence bond crystal rather than a spin liquid. So I should probably make that clear, but
so the gapped one will be the one which you are calling as the chiral spin liquid? Sorry.
So we would hope that this, yeah. So even with a gap, there are different possibilities. That's right. So there's the gapped chiral spin liquid is our favorite, which we hope is here, but I can't tell you that they've definitely seen it. But there's also the gapped Z2 spin liquid is another kind of gapped spin liquid, which is different because it doesn't break time reversal symmetry. It doesn't have an edge state. Those are ways in which it's different from the chiral one. And then finally, you could have a gap state which breaks spatial symmetries. That would be like a valence bond crystal. That's basically like a crystal of singlets. So there are many different possibilities that all have a gap, but they all do differ in principle in experimental signatures. It's just been hard to do those in this particular compound. So, I mean, I think these organics seem to be quite difficult in some ways to work with. There is another family, like actually this thing I mentioned at the bottom, there's another family that several groups have been studying of triangular lattice compounds. I mean, there are many families, but I don't think there is agreement yet. So for example, in the family that we were working on, and there's now a paper on the archive, it's like potassium, ytterbium, selenide. It seems that we think it is a critical point to a gap spin liquid, but there's another paper that thinks it's actually a gapless spin liquid. So it's still and there the challenge is those are neutron scattering experiments, and it's very hard to get from, even if you think you know what the phase is, to be able to predict the neutron scattering spectrum with high accuracy.
So the high pressure will be a difficult thing, is it, to tune this?
It's worth trying. I mean, yeah, I'm not sure. Like, I do think pressure is a great tool. Like, for example, for that compound I just mentioned, if pressure could move you away slightly from the critical point, like for example, we would be predicting a larger change under pressure probably than the other group would. But I don't think anyone has done it under pressure yet.
Okay, thank you.
The next question is by Mithun.
Hello. So can you hear me, sir?
Yes, we can not hear you very well. So can you speak a bit?
Yeah, actually, I have a question from the experimental data that you have shown on tantalum arsenide, the polar pattern. Okay, so from that paper, actually, this one. From this paper, actually, from the theory side, you have actually related the second harmonic signal to the shift current, right? Shift current that comes from the topology in the band structure. Hello.
Yes, yes.
Yeah. So could you please explain how you are relating the shift current with topology, meaning that you are giving an omega and collecting 2 omega. So how do you relate this one?
Well, the one thing, okay, so the one thing we were able to do on this problem is a little incomplete, but you can make a relation between the integral over frequency of the second harmonic generation, like a sum rule. So if you integrate that over frequency, you can relate it to the skewness, the third cumulant of the Wannier functions. I think that's the one theoretical statement we had. So it's true that here, I showed data at one particular frequency. It's over a fairly broad frequency range, but the theory argument that we have would not really predict that super accurately. I mean, it would just say that there's a large magnitude somewhere. This third cumulant is kind of neat, though, because we sort of know that the first cumulant, like the center of mass of the Wannier function, tells you the polarization. But then even if you know where the center of mass is, there could be another kind of inversion breaking, which is that the shape is very asymmetric. And that is what turns out to matter for second order optics. That's kind of the point of what we said. But just to be clear, we don't know how to connect this to the Weyl-ness. In other words, we think of tantalum arsenide as having this very large effect because it's very polar, in a sense that the wave functions clearly point in one direction, I guess. But I don't think it is so directly tied to it being a Weyl semimetal. I mean, I don't know if other people agree on this, but that was our interpretation.
No, sir. Actually, just physically, is it possible to relate? Meaning, you have a shift current generated, and how is it really connected to the 2 omega that is coming out? Is it?
Yeah. So I don't think there's any universal relationship between shift current. Okay. Let me think about this. I don't think that the shift current at zero frequency has to be related to the nonlinear, to the second harmonic generation at any particular frequency. I mean, maybe it could be that there's a relationship between the shift current and the integral over frequency of the second harmonic. That's all I can think of, but I'm not even sure that that exists.
Okay. And this calculation, is it done explicitly for the 112 plane, or because the crystal was cut in 112 plane?
Yeah, so there's a second paper by Ornstein that we're on that has a little bit, that has our best effort at theory. So okay. In other words, this was a Nature physics paper, and then later on there was, I think, a Physical Review B, which has a lot of details and that's the one that has this theory sum rule I mentioned, but I don't think I know anything beyond what's in that paper.
Okay, thank you.
Okay, more questions? Okay, if not, let's thank Joel once more for this nice talk, and thank you, Joel, and hope to see you at some point, and good night. Sorry for the late night for you.
Great, thank you, my pleasure.
Bye.